This is a presentation on the topic process management in Android. Let's dive right into it. Firstly, let's see what process and application fundamentals in Android are. An Android application is simply a software designed to run on an Android device or an Android emulator of some kind. They can be written using the languages Kotlin, Java, and C++. And by default, all components of the same application run in the same process. And most applications should not try to change this. However, if we find the need to control which process a certain component belongs to, we can do so in the manifest file. So there are four app components in Android. Those are firstly, an activity is the entry point for interacting with the user. It represents a single screen with a user interface. For example, an email app might have an activity that shows a list of new emails, another activity to compose an email, and so on. A service, however, is a general purpose entry point for keeping an app running in the background. So for example, a service might be playing music in the background while the user is on a different app. A broadcast receiver is a component that enables the system to deliver events to the app outside of regular user flow, allowing the app to respond to system-wide broadcast announcements. So, for example, an app can schedule an alarm to post a notification to tell the user about some upcoming event, and by delivering that alarm to the broadcast receiver, there is no need for the app to remain running until the alarm is going off. A content provider manages a shared set of app data that we can store in the file system, for example, in an SQLite database, on the web, or any other persistent storage location that our app can access.
Now let's discuss process and application lifecycle. In most cases, every Android application runs its own Linux process. When an application needs to run, we create its process. This process continues running until it is no longer needed. After it ends, the system reclaims its memory. A fundamental feature of Android is that an application process's lifetime is not directly controlled by the application itself. Instead, it is determined by the system through a combination of components of the application, how important these things are to the user, and how much overall memory is available. Now let's discuss what is activity stack. When a new activity starts, it is pushed on the top of stack and takes focus. The previous activity remains in the stack. System retains the current state of its user interface before pushing it to the back of stack. When the user performs back action, the current activity is popped off the stack and previous activity resumes. Now let's discuss life cycle of an activity. This diagram shows the important state paths of an activity. There are three key loops in this life cycle. The first one being the entire lifetime. It is defined as the period between the first call on create to on destroy. We may think of this as the time between setting up the initial global state for the app and the release of all the resources associated with the app. The second loop is visible lifetime. It is defined as a period between the call on start and on stop. The app may not be directly visible and interacting with the user at any one time if it is not in the foreground. The feature that distinguishes this lifetime is that even if not in the foreground, the app maintains resources such that user can instantaneously switch to this app. The third one is the foreground lifetime. It is defined as the period between a call to on resume to on pause. During foreground lifetime, the activity is in front of all other activities and interacting with the user. Now let's discuss lifecycle of a service. In Android, services have two possible paths to complete its lifecycle, namely started and bounded. Started service. It performs a single operation and doesn't return any result to the caller. Once this service starts, it returns in the background even if the component that created it destroys. A service becomes started only if an application component calls start service system call. Second one is bound service. It gives a client-server relation that lets the component interact with the service. The component can send requests to services and get results. A service is bound only if an application component binds to it using bind service system call. Android assigns each process a place in importance hierarchy based on the components operating in it, and it uses the state of those components to determine which process should be killed when memory is low. These processes in the decreasing order of importance are as follows: foreground process, visible process, service process, and cache process. Now let us understand the definition of these processes. First, the foreground process. These processes are the ones which are on top of screen and with which the user is interacting. When some application needs permission like storage access, etc., a dialog box will appear and ask for the required permission. So at this time, the process corresponding to the activity of the app which is running previously will go in the visible state. Service processes. These are not visible on screen but are doing some task important to the user in the background. The last is the cache process. These are the processes which are not currently needed for efficient switching. Multiple processes are kept in cache states. Now let us try to understand the conditions under which these processes are killed. Since these processes are in decreasing order of importance, hence the basic rule is that the lower ones are killed for the sake of running the processes above them. Other than this rule, there are few other things that should be noted. The first one being that the service processes are demoted to cache processes if they are running for long time, so that they don't keep taking resources. Second, a well-running system has multiple cache processes so that we can resume those processes at any time. Now we'll try to understand how threads work in Android system. When an application is launched in Android, it creates the first thread of execution known as the main thread. The Android allows an application to have multiple threads of execution running concurrently. The threads have various properties. The first one is every thread has a priority. Threads with higher priority are executed in preference to the threads with lower priority. The thread can exit by two methods. When exit call method of class runtime is called, and also the security manager has allowed it. Second, all non-daemon threads have died by throwing an exception or by returning the call to run.
Okay, so let us now see how inter-process communication happens in Android. So there are two ways processes communicate with one another in Android. First is using intents. An intent is used to perform an action on the screen, mostly to start an activity, send a broadcast receiver, or start services, or send messages between two activities. Second is using AIDL, which allows us to define the programming interface that both the client and service agree upon in order to communicate with each other. Let's move on to deadlocks. Firstly, a deadlock occurs when the following four conditions are holding simultaneously. First is mutual exclusion, which means only one process at a time can be holding a resource. Second is hold and wait, which means a process holding at least one resource is waiting to acquire additional resources which are held by other processes. Third is no preemption, which means that a resource will only be released by a process when the process has finished completing its task. Fourth is circular wait. Now, as the name suggests, it means that the processes are cyclically waiting for one another to finish and release their resources. And there are three ways in which most operating systems deal with deadlock. First is to prevent or avoid the deadlock. Second is to detect the deadlock and recover from it. Third is to simply ignore the deadlock. And Android operating system tries to detect the deadlock and tries to recover from it. So for the deadlock detection algorithm, what we're trying to do is we basically fulfill the requests one by one wherever the requested resources can be made available from the available resources. And we do this for every process for whom it is possible. And if we're able to finish all the requests, so we're able to fulfill all the requests, then there is no deadlock. Otherwise, the system is in a deadlock state. And for recovery, we need to roll back to some previous safe state and restart the process from that state.
I am Mayank, and I will talk about the scheduling policy in Android. So Android is largely based on Linux, and so is its scheduling policy. Now, Linux is a fairly complex operating system. It uses several different scheduling policies in different situations. The ones majorly used from them in Android are FCFS, Round Robin, and Completely Fair Scheduling Policy. FCFS and Round Robin are used for real-time urgent processes like those related to hardware, example audio and video. For all the other ordinary processes, Completely Fair Scheduling Policy is used. Now, what is CFS or Completely Fair Scheduling Policy? It has been in the Linux since version 2.6.23 and it handles IO and CPU bound processes very elegantly. The main idea behind CFS is the ideal fairness policy, which says that if there are n processes waiting to be scheduled, each process will get 100 by n% of the total CPU time. Say there are 4 processes, each of them gets 25% of the total time in a particular time quantum. Okay, that is the main idea behind CFS. Now how it happens in Android in real life is shown here. There are several runnable processes in any operating system at a given time. These processes are associated with a nice value and a variable v runtime. Now what are these nice values? These are numbers which vary from -20 to 19 in Android. They are allotted such that a higher priority means lower nice value. So they are allotted to all the processes and some examples are given here. For example, background processes have a nice value of 10 and foreground have a -2 value. So this means foreground has a higher priority, which is understood because that is what the user is currently interacting with. Okay, that's about nice value. The other variable v runtime is initialized at a minimum value, default value at the beginning for every process. Now, at every context switch or scheduling point, if the currently running process had run for t milliseconds, then its variable v runtime will be incremented by t multiplied by a weight associated with its nice value. So this should mean that a lower nice value process will have so slow increase in v runtime compared to higher nice value process. Now, these processes are arranged in a red-black tree data structure according to their v runtimes. Processes on the left have v runtimes less than processes on the right. So the leftmost process will obviously have the least v runtime. This is the process which will be run at the next context switch or this context switch. It is also cached in a variable by the name min v runtime so that it can be accessed in constant time. Now the process which was running previously, if it is still runnable, it will be added into the red-black tree with its new v runtime, which is computed here. And now what all this is actually doing is the processes which have a higher priority will see slow increments in v runtime due to lower weight and hence will get more chances to execute. So this scheduling policy in theory should provide a good user experience, but practically it was observed that the less relevant background processes still take up significant CPU resources, and that limits the foreground processes and it impacts the user experience. To mitigate this, Android used another feature from Linux kernel, which is control groups. Now what are these control groups? They are a Linux kernel feature which organize processes into hierarchical groups whose usage of resources can be limited and monitored. Example, all background related processes can be grouped into a background C group and a limit on the max resource usage can be set on them. Some of the different C groups are shown here. They are arranged according to their priority levels. The background non-interactive processes or threads have a lower priority compared to the foreground processes or threads and so on. So one example of limit on the C groups is that the background C group threads can use only 1% of total CPU. So that foreground CPU are completed without delay and the user gets a better foreground experience. Actually, these C group levels in Android are handled by two different subsystems, SCHEDTune and CPU set. Now, what they do are SCHEDTune mainly allocates CPU resources and triggers CPU boost. And CPU set binds a process to a specific CPU and memory nodes. These are essentially to limit the resource usage. So Android mainly uses the CFS policy and C groups with some more techniques to handle process scheduling and process resource management. That's about our presentation. Thank you.